You might not be completely done with these, but let's take a look and see how you're doing on them so far. So for number one here, the key phrase is right there, simple interest. So for simple interest, our interest formula is I equals PRT, principal times rate times time. So to find the amount of interest, we have our principal here of $2,500 times our rate, 3%. That has to be written as a decimal to be a rate, is 0.03. And our time is 6 months. Well, remember we said time is always given in years. So 6 months is 6/12 or 1/2 of a year, however you prefer to write it. That should give us $37.50. And it does. We get $37.50 in interest. But it didn't ask for the interest. It says find the maturity value. So that maturity value or future value, whichever way you want to call it, is the principal of $2,500 plus the interest of $37.50. So we get an ending value of $2,537.50. The second one I expected to be a little bit more of a struggle. The key phrase here is compounded monthly. Monthly means it is 12 times a year, so that would be n equals 12. And I never actually gave you this formula yesterday. We talked about it, and we plugged numbers into it, but I never gave you the formula itself. That future value or maturity value of compound interest is the principal times 1 plus our rate divided by n, where n is the number of times in a year, so monthly is 12, the power of n times t, where t is our years. So for this formula, the principal is $4,000 times 1 plus 6% as a rate is 0.06, divided by, since it's compounded monthly, it'll be divided by 12. Close our parentheses to the power of 12 times 2 years. 4,000 times, open parentheses, 1 plus 0.06 divided by 12, close parentheses to the power of 12 times 2. $4,508.64. So that is the ending balance, not just the interest. That's what you would have at the end of those 2 years. Any questions on those? Okay. So what we want to do here today is we want to wrap up Unit 2. Remember, tomorrow is the Unit 2 test. Like I said, if you don't want to log into class tomorrow, that's okay. That's your work from home day anyway. As long as you have the test completed sometime during the day tomorrow, that is fine. I will be online on the network during class for at least the first 20 to 30 minutes in case you have any questions and you want to pop in and ask them. Otherwise, tomorrow there won't be any new material or any lecture tomorrow. Also, make sure Quiz 5 is turned in. That was actually due yesterday. A couple of people don't have it in yet, so make sure you get that turned in as well. So our last topic I want to talk about here for Unit 2 is things that look like this. Of course, what does that mean?
8 to the power of 3.
8 to the power of 3. Perfect. How would we calculate it?
8 times 8 times 8.
8 times 8 times 8. Very good. That's 8 to the power of 3, and it means that we have 3 eighths multiplied together. Comes out to be 512. This is a form of an exponent. And in that form, our exponent has two parts. It has the base, which is the number that's being acted on here, in this case the 8, and it has the power, which tells us how many times that base is going to multiply itself. So 8 to the third means 3 eighths multiplied together. Now on your calculator, doing 8 times 8 times 8 isn't that bad for only 3 of them. But if you have something like 2 to the power of 11, you don't want to try to sit there and punch 11 2's into your calculator. So we need a shortcut for doing that. And we've seen it on the calculator. As we saw, it's that caret key. Or, depending if you have a Casio or Sharp, it might be X to the Y or Y to the X. Or X to the box. If you use that key, of course, 2 to the 11th power comes out to be 2048. Well, what I want to look at today is reversing those. We've said that all of our operations come in pairs. They're called inverse pairs. And by inverse pairs of operations, what I mean is they're set up so that one undoes the other. You know, if we have just pick a random number like 11, if I add 4 to 11, I get 15. Well, if I want to get back to the 11, I take my 15 and I subtract 4. I get back to 11. Adding 4 and then subtracting 4 reverse each other. And the opposite is true. If I started out with 11, if I subtracted 4, I would get 7. If I want to get back to that 11, I take my 7 and I add 4 to get back to 11. Addition and subtraction are an inverse pair. If I add a number and then I subtract the same number, I get back to where I started. Or if I subtract a number and then add the same number, I get back to where I started. Multiplication and division are also an inverse pair. Let's say I start with the number 12. If I multiply by 3, I get 36. Well, if I want to get that back to the 12, I take my 36 and I divide by 3. It gets me back to the 12. Multiplying by 3 and then dividing by 3 get me right back to where I started. Or if I did 12 divided by 3 would give me 4. If I want to get back to the 12, I take my 4 and I multiply by 3 to get back to 12. Multiplying by a number, then dividing by the same number, reverse each other. The same as if I divide by a number, then multiply by that number. They're inverse pairs. Everything in math is reversible to some extent. So if we have something like 7 squared, that of course means 7 times 7, which is how much?
I don't know.
49, yep. So 7 times 7 is 49. If I want to reverse that, what we use is a root, a square root. Now that symbol is actually called a radical symbol. And most often when we see it, it is seen as a square root. The square root of 49 is 7. And the reason that is because 7 squared equals 49. It's just reversing that calculation. That radical symbol actually has two parts to it as well. It has a part inside here, which is again called its base. That's the number being operated on. There's a number up here that is called, not its power now, but it's called an index. That tells us what power is actually being reversed here. If there's no number there in the index, it's assumed to be a 2. It's a square root. So the square root of 64 is asking us what number squared equals 64? Now, this is not as straightforward as you would think because we've done our negative numbers now. We know that 8 squared equals 64. But we also know that negative 8 squared, a negative times a negative is a positive, is also 64. So technically the square root of 64 is 8 or negative 8. Just like up here, the square root of 49 is technically 7 or a negative 7. Now for our purposes, we're just going to put down the positive answer in most cases because that's what we're really concerned with is the positive answer. In everyday life outside of your checkbook, not a lot of negative numbers to deal with. What if I have something like 5 to the power of 3? Well, that's 5 times 5 times 5, which is 125. Well, we said these roots can reverse any power. To reverse a power of 3, we have what's called a third root, or a cubed root. The cubed root of 125 is asking us what number to the power of 3 is 125. We just saw that 5 to the power of 3 is 125. We're here. Is negative 5 to the power of 3 125? Well, no, it's not. That'd be negative 5 times negative 5 times negative 5. Negative 5 times negative 5 is a positive 25. But I multiply by another negative 5. Positive times a negative is a negative. I get a negative 125. So for the third root of 125, it is just 5. Because negative 5 to the third power is not a positive 125. It's negative. Or if I do 5 to the fourth power, it's 4 5s multiplied together, which is 625. So again, I look at a fourth root. The fourth root of 625, again, that's asking me what number. The power of 4 is 625. Well, we just saw over here that 5 to the power of 4 is 625. But is negative 5 to the fourth power 625? Negative 5 times negative 5 times negative 5 times negative 5. Well, we just saw up above that the first three, the negative 5 to the third power, multiplies to a negative 125. If I multiply by another negative 5, a negative times a negative is a positive 625. So yes, negative 5 to the fourth power is a positive 625. So this is 5 or negative 5 for this one. Let's go one more step here. Let's go 5 to the fifth power, which of course is 5 5s multiplied together, otherwise known as 3,125. So if I ask what is the fifth root of 3,125, it's just asking me what number to the fifth power 3,125. All we just saw, that is 5 to the fifth power. But once again, do we have to worry about negative 5 to the fifth power? 5 negative 5s multiplied together. Again, we saw up above that the first 4 multiplied to be a positive 625. Well, if I multiply that by one more negative 5, a positive times a negative is a negative. Negative 5 to the power of 5 is a negative 3,125. We're probably seeing a pattern develop here. The even powers always give a positive result. For the odd powers, if we have a positive base, we get a positive result. Remember, base is that number it's acting on, the positive 5 or negative 5 for these examples. If we have a negative base, we get a negative result. Because of that, it gives us a weird thing when we try to take roots of our negative numbers. Let's try to do the square root of a negative 16. Well, you might want to say negative 4, but let's think about this. What number squared equals a negative 16? Well, we just said above, if it's an even power, the result is always positive. There's absolutely nothing that we can square that's going to give us a negative result. There is no solution for this. No answer for that. If we were to try to put that in our calculator as a square root of negative 16, our calculator spits out an error saying we did something wrong. Now, at this level, we're saying there is no solution to the square root of a negative number. If you were to go on to a 4-year degree somewhere, you would most likely have to take an intermediate algebra course or a college algebra course. In that type of a course, they actually do define the square root of a negative. They use what's called complex and imaginary numbers. What it is they made up a number that is the square root of a negative, and they defined a whole system of algebra around that. We're not going to get into that. They're called imaginary for a reason, because we just imagined them. We just made them up. We're going to stick in the real numbers for our part. For our purposes, there is no square root of a negative number. However, a third root, if I want to do a third root of a negative 125, well, we saw up above, negative 5 to the third power is a negative 125. So the third root of a negative number is just a negative number. Third root of a negative 125 is negative 5. We can do a third root of a negative number, even though we can't do a square root. So how about a fourth root? Well, let's say we do a fourth root of 81, of negative 81, I should say. That's asking us what number, the fourth power, is a negative 81. Well, again, there's no solution. Because up above we said if it's to an even power, the result is always positive. There is nothing that we can take to a power of 4 and get a negative number. It just doesn't happen. Let's go one more. So the fifth root of negative 243. So this is asking us what number to the power of 5 is a negative 243. Since this is an odd power, we know that we can have a negative base and get a negative result. Actually, negative 3 to the power of 5 is negative 243. So the fifth root of a negative 243 is a negative 3. So the pattern you see developing here is if it's an even root, like a square root or a fourth root or a sixth root or so on, we cannot take the even root of a negative number. It doesn't exist. But the odd roots, third root, fifth root, seventh root, we can take those of negative numbers because of that even and odd power relationship. We're not going to do anything other than square roots in this class. To do a square root, most of you it's going to be a second function on your calculator. Many of you have an x squared key on your calculator that looks like that one in red there. If you look above it, you see the square root symbol. So to enter the square root, you do second square root, then type in the number. If we want the square root of 64, we type in 64. And you hit enter. It spits out the 8. So that is all we have for our topics for test 2, or for unit 2. I wanted to take the last few minutes of class here today to review a little bit for this test. The topics, first of all, for the test. Obviously, fractions. And you need to be able to convert mixed numbers. To improper fractions. And the other way around, improper fractions back to mixed numbers. You need to be able to convert from a fraction to a decimal. And back again. You need to be able to reduce a fraction. And you need to be able to rename a fraction. If I give you 3/4 and I ask you how many 20ths is that, you need to be able to do that change, to make that name change. And then, of course, operations with fractions. Add, subtract, multiply, divide fractions and mixed numbers, of course. Decimals. The same laundry list. Convert decimals to fractions, fractions to decimals. Do operations with our decimals. And percents. You need to be able, again, to convert from a percent to a rate, which is just the decimal form. Or to a ratio, the fraction form. And then, of course, back from rate back to percent and from ratio back to percent. And, of course, to calculate percents. Very, very careful with percent increase and decrease. I want to do a couple examples of those. Let's say after 6% tax, Kim pays $265 for supplies. How much did Kim pay in tax? The common mistake here is to find 6% of the 265. Doesn't work that way. The 6% did not come from the 265. It came from that base amount, the starting amount, the price before tax. Then we added the tax to that to get the amount paid. As you recall, each of these had percents and dollars that described them. We look at the percents. The amount before tax is 100%. The tax is 6%. It's the amount plus tax, so the amount that was paid was 106. 100 plus 6. You get 106%. The 265 represents the amount paid. So that 265 goes with 106%. So we can use that 106% here as 106 over 100. The 265 goes with the 106. and we cross multiply and divide. 100 times 265 divided by 106 gives us 250. 250, now that represents the same thing as the 100%. That was the amount before tax. But what we're asked for here is how much was the tax? This amount. That's the difference between those two. We take the 265 as the amount paid, we subtract the amount before tax, and we get $15 in tax. Had we found 6% of the 265, we would be off by about 90 cents. Won't quite work out. Other examples I wanted to make sure to show you deal with converting our decimals back into fractions. If I ask you to convert to an exact fraction or just convert to a fraction, for numbers like let's do 0.85 inches and 0.324 inches. 0.85, I'm going to make that 85 hundredths, so 85 over 100. Now reduce it. Both of those divide by 5. 85 divided by 5 is 17. 100 divided by 5 is 20. As an exact fraction, 0.85 is 17/20. For the 0.324, I do 324 over tens, hundreds, thousandths. 324 over 1,000. And I can reduce. Both of those reduced by 4, giving me 81 over 250. I think that's as far as I can go with that one, 81 over 250. So as an exact fraction, 0.324 inches is 81 over 250 inches. But we often find that those exact fractions aren't very useful to us. So we might say convert to the nearest if we're asked to do that, let's do our 0.85 inches again and 0.324 inches. It's a very different process. Doesn't look anything like what we did to convert it to an exact fraction. Here we take the 0.85. Notice we still have the decimal in it. Up here, the first thing we did was remove the decimal point, and we gave it the appropriate denominator for the number of decimal places that it used to have. Here, we're not going to do that. We're going to keep the decimal point in it exactly where it was before, and we're just going to put it over a denominator of 1. Well, we want the denominator to be 16, so we're going to multiply that 1 by a 16 to make 16. If we multiply the denominator of a fraction, we have to multiply the numerator of the fraction. So 0.85 times 16 is, what is that, 13.6? It is 13.6 over 16. Well, this is telling us that we are between 13 sixteenths and 14 sixteenths. Well, 13.6 is actually closer to 14, so that's 14 sixteenths, which are reduced to 7/8 of an inch. We do the same thing for our 0.324. We leave the decimal in it, and we just put it over 1. And again, we want it to be 16ths, so I'm going to multiply by 16 on bottom. First, I have to multiply the numerator by the same thing. So 1 times 16 is 16. 0.324 times 16 is 5.184. That is telling us that we are between 5 sixteenths and 6 sixteenths 5.1, that's closer to the 5, so that is 5/16 of an inch. That is a process, those last two problems there, that I would say is the most missed question on this Unit 2 test. Partly because there wasn't, I think there was one example of it in the homework was all there was. But it's a very important skill, especially if you're looking at matching up tools to a calculated number. You're calculating numbers to 3 or 4 decimal places, but your tools might go to the 64th or the 1/28th of an inch. You need to be able to convert those decimals into a fraction with the denominator that you want it to be. That's an important skill to have. So with that, that wraps up Unit 2 for us. So our homework for today is page 93. 1 through 21, the odd. And of course, remember, at some point tomorrow, do the test. As I said, I will be in class tomorrow. I'll be logged in. If you have any questions or need help with anything on the test, I'll be here. Otherwise, log in at any point during the day. You don't have to log into Blue Jeans. Go to Blackboard at any point during the day, access the test, and complete it. And that is all that's required of you for tomorrow. Any questions? Okay, then. Well, I will turn you loose if you want to spend the next